In this video, we're going to be talking about converting from the equilibrium constant in terms of concentration, K sub C, to the equilibrium constant in terms of partial pressures, or K sub P. Say we have the fictional reaction A plus 2B goes to C, and this is an equilibrium. And let's say that this whole reaction is in the gas phase. So all of our reactants and products will make it into our gas law. Remember that pure solids and pure liquids do not go into either Kc or Kp. So if we're thinking about defining our equilibrium constant, capital K, in terms of concentration or molarity, what should we do? So we'll always put the products over the reactants, and remember that any stoichiometric coefficients are going to make it into our expression as exponents. So we'll have C squared because C is our only product, and that concentration should be squared because of the 2 in the balanced equation, divided by the concentration of A times the concentration of B squared. And again, that squared is coming because the reactant B has a 2 in the balanced reaction. And now if we wanted to express K sub P, which is the equilibrium constant in terms of partial pressures of each component, what would that look like? Well, this would also be products over reactants, and again, the stoichiometric coefficients from our balanced reaction are going to appear as exponents. So we'll have the partial pressure of C squared divided by the partial pressure of A times the partial pressure of B squared. But if we have Kc, for instance, and we wanted to convert to Kp, how are these two equilibrium constants related mathematically? To determine that, we'll need to look to our ideal gas law. So recall the ideal gas law is pressure times volume equals number of moles times the gas constant times temperature. So PV equals nRT. Note that molarity is number of moles divided by number of liters, or N divided by V. It's moles divided by volume. So we can think of N over V as molarity, and we can rearrange our ideal gas law to be pressure equals N divided by V, or molarity, times RT. And if we have moles of just one component of our reaction, then the ideal gas law will give us the partial pressure of that one component. So for instance, if we had N sub C, or the number of moles only of C, then our pressure here that we're calculating would be the pressure of C, or the partial pressure, P sub C. So then if we're thinking about Kp, we could write our Kp, remember the pressure of C is just the molarity of C, or N over V, times RT, but both of those will need to be squared because the partial pressure of C should be squared. So we'll have concentration of C squared times RT squared. On the bottom, we could replace the partial pressure of A with the molarity of A times RT, and we could replace the partial pressure of B squared with the concentration, or molarity of B squared times RT squared. All of these R's and T's are the same. Can we cancel any of them out? Absolutely, we could cancel out RT squared divided by RT squared. Note also that C, concentration of C squared divided by concentration of A times concentration of B squared is simply K sub C, or the equilibrium constant in terms of concentration. And then what we're left with is 1 over RT. So we have Kc divided by RT equals Kp for this particular reaction. Note that this conversion is going to be a little different depending on your reaction. The more general form of how we can convert Kc to Kp is that Kp equals Kc times RT all raised to delta N, where delta N is the change in the number of moles in the gas phase between the products and the reactants. So it's the number of gas moles of product minus the number of gas moles of reactant. Since everything in our reaction was a gas, we have 2 moles of gas as product, because they're both C, minus 3 moles of gas of our reactant of A and 2b. And so 2 minus 3 gives us a negative 1, which would in fact give us kc rt to the negative 1, or kc divided by rt, which is what we got before.